Minus 45 degrees Celsius. That is not a weather forecast. That is a weapons-grade cold. The kind that freezes exposed skin in minutes. That turns diesel fuel into gel. That makes steel brittle enough to crack like glass. And somewhere in that darkness, right now, a freight train is moving through it. Not slowing down. Not waiting for morning. Moving through the Alaskan interior at speed. Hauling thousands of tons of freight that cannot wait for the temperature to rise. In the cab at the front of that train, one man. Watching the track ahead. Managing a locomotive that was never designed to operate in conditions that are trying to kill it. This is one night of a train engineer in Alaska at minus 45. And by the time this video ends, you will understand exactly what that night costs, what it demands, and why the train runs anyway. I'm going to assume something about you. You have complained about cold weather before. Maybe your car would not start. Maybe your pipes froze. Maybe you decided not to go outside because the temperature was uncomfortable. And while you made that decision, somewhere in Alaska, a man climbed into a locomotive cab and pointed it into darkness at minus 45 degrees Celsius. Not because he wanted to, because the freight behind him has a delivery schedule. Because the communities ahead of him depend on what that train is carrying. Because the railroad does not close because of cold. The cold is not a reason to stop. The cold is just a job. You need to understand what minus 45 actually is before you can understand what it does to a train. At minus 40, which is the point where Celsius and Fahrenheit are the same number, diesel fuel begins to gel. The wax crystals that are always present in diesel solidify. The fuel thickens. Flow rates through injectors drop. Engine power decreases. In severe cases, the fuel system blocks entirely. At minus 45, steel becomes measurably more brittle. The molecular structure of metal changes its response to impact stress. A rail that would flex under a wheel at 0 degrees Celsius may crack at minus 45. Not visibly, not dramatically. A hairline fracture. Invisible from the cab. Invisible from a track inspection vehicle. Present only in the material, waiting for the stress of a loaded freight train passing over it. At minus 45, air contracts. The compressed air system that operates the brakes on every car in the train, the system running through a pipe the entire length of the consist, begins to leak at every joint and seal. Cold makes rubber rigid. Rigid rubber does not seal. The brake pipe pressure drops. The engineer compensates. But there is a limit to how much compensation is possible before brake performance is genuinely degraded. At minus 45, lubricants thicken. The grease in wheel bearings. The oil in gear cases. Every lubricant on every rotating component on every car in the train is performing at a fraction of its designed efficiency. And the engineer in that cab knows all of this. Not from a manual, from experience. From the way the locomotive feels at these temperatures. From the instruments that are telling him things that instruments at normal operating temperatures never have to say. He is not just driving a train. He is managing a machine that the temperature is actively trying to disable. Here is what most people never think about. The locomotive was designed in a factory, tested in a controlled environment, certified to operate within a temperature range. Minus 45 Celsius is at or beyond the edge of that range. And the locomotive knows it. The diesel engine inside a freight locomotive at these temperatures faces a problem that starts before the engineer even begins his shift. The engine cannot be allowed to cool completely overnight. A large diesel engine that is cooled to minus 45 Celsius and then is started cold accumulates more wear in the first minutes of operation than it accumulates in hours of normal running. The oil that was protecting every bearing surface has drained from those surfaces overnight. It is thick, cold, slow to pump, and the engine needs to run before the oil reaches the temperature where it flows properly. This is why locomotives in extreme cold climates run continuously. Not because anyone forgot to turn them off. Because turning them off in these temperatures means destroying them slowly every time they are restarted. Railroads have learned to equip locomotives with automatic start-stop systems and auxiliary power to keep engines warm even when they're powered down. Union Pacific, but in genuine extreme cold. Many engineers and dispatchers simply do not shut the locomotive down between assignments. The fuel cost of idling through the night is less than the maintenance cost of a cold start at -45. The fuel heaters run continuously, heating the diesel in the tanks and lines before it reaches the injectors, maintaining the fuel at a temperature where it flows, where it burns, where the engine can produce the power the train requires. The cab itself is heated, but the cab heating system on a locomotive was not designed for -45. It was designed for normal cold. At these temperatures, the cab heater runs at full capacity and produces a temperature inside the cab that is warm enough to work in, but not comfortable in the way most people understand comfortable. The engineer dresses for it. Layers. Not because the cab is unheated, because the cab heating is fighting conditions it was not designed to beat completely. Now here is the danger that the engineer cannot see. The track. Steel becomes relatively brittle at cold temperatures. This means that extreme cold can cause rails to split or crack. Trains, a rail that has been in service for years, carrying millions of tons of freight through summer heat and winter cold, has accumulated invisible internal stresses, microfractures that formed and stabilized over years of thermal cycling. At -45, those stresses intensify. The rail contracts. Welded rail sections that were laid at a design-neutral temperature are now under tension far beyond what the designers specified for that particular installation. Constant patrols are made before each train is allowed to proceed. Alaska rails, on some sections of the Alaska Railroad. Track maintenance crews in heated vehicles moving ahead of trains, looking for the visible signs of rail problems. A gap where there should be no gap, a kink where the rail has buckled under thermal stress, a section where ice has formed between the rail and the tie in a way that has lifted the rail from its design position. But the inspector in a vehicle moving at 30 kilometers per hour cannot see everything that the freight train moving at 60 will encounter. The inspection is the best available protection. It is not a guarantee. The engineer knows this. He knows the track sections on his route. He knows the ones with history. The ones where problems have appeared before in extreme cold. He carries that knowledge as a constant background awareness. Not anxiety, not fear, but operational understanding. The informed respect of someone who has been doing this long enough to know that the track underneath is not passive infrastructure. It is a system under stress. Air brakes undergo temperatures ranging down to -45 degrees Celsius, and research has quantified brake system failures in extreme cold weather. National Research Council Canada. The brake pipe running the length of the train is losing pressure faster than it would at normal temperatures. The engineer checks his brake pipe pressure more frequently than he would on a summer run. He knows the threshold below, which he needs to stop and investigate before continuing. Because a train that cannot stop in the distance available is a train that has lost the only protection that matters. Here is the layer that transforms this from an engineering story into something more. Alaska is not served by a road network the way the lower 48 states are. Many communities along the Alaska Railroad corridor have no road access, no highway, no way to receive freight except by rail or air. And air freight at these temperatures is expensive, unreliable, limited in capacity. The train is not a convenience for these communities. It is the supply line, the fuel that heats homes, the food that stocks shelves, the equipment that keeps facilities operational through an Alaskan winter. When the train does not run, communities feel it, not immediately, but within days. The margin between what is in storage and what is needed is measured in days, not weeks, in the most remote locations. This is what the engineer in that cab is carrying. Not just freight, the operational reality of communities that have no alternative. And this is why the railroad does not close at -45. Why the engineer does not stay home because the temperature is dangerous. Why the locomotive runs through conditions that the people who designed it never fully anticipated. Because the alternative, a railroad that stops when the cold is worst, is a railroad that fails the people who need it most precisely when they need it most. The cold is worst in January and February. The communities need fuel and supplies in January and February. The train runs in January and February. The economics and the human need point in exactly the same direction. If you are still here, you are already seeing something about what it takes to keep freight moving through conditions most people never experience. Subscribe now, because what comes next is what happens when the system reaches its limit. The cold does not always lose. Nothing works when it's minus 40 degrees out. Global Railway Review, said one railroad operations manager describing a polar vortex event. Trying to turn something with a wrench, with all the clothing you have on, makes it so much more difficult. Global Railway Review. Equipment fails in extreme cold in ways that do not fail at normal temperatures. A switch, the mechanism that redirects a train from one track to another, freezes. The electric heaters designed to keep it clear of ice cannot overcome the rate of heat loss at minus 45. The switch cannot move. The train cannot proceed on its planned route. A crew must go out into the darkness and the cold and manually clear the switch. In conditions where exposed hands lose dexterity in minutes. A brake hose, the rubber connection between cars and the consist that carries the compressed air for the braking system, cracks from the cold. The brake pipe pressure drops. The train must stop. The crew must identify which hose has failed. In a train of 100 cars in darkness at minus 45, walking the length of that train is not a routine task. It is a physical ordeal. A wheel bearing, its grease thickened to the point of marginal lubrication, begins to overheat from the friction of inadequate lubrication. The hot box detector beside the track registers the elevated temperature as the train passes. The dispatcher calls the engineer. The train stops. The bearing must be inspected. Possibly the car must be set out, uncoupled from the train, and left at the nearest siding until a maintenance crew can reach it. Trains are shortened when temperatures dip below minus 25 Celsius to ensure brake pipe pressure remains consistent throughout their entire length. Press reader, the train the engineer is running tonight is shorter than the trains that run this route in summer. Not because there is less freight to move, because the physics of extreme cold have imposed a limit on how long a consist can be and still maintain safe braking performance. Every one of these limitations is a cost. To the railroad, to the shippers, to the communities waiting for freight. The cold does not destroy the system, but degrades it continuously, relentlessly, for as long as the temperature holds. It is 3 a.m., the darkest hour, the coldest hour, the hour when human alertness is at its daily minimum regardless of how much sleep was taken before the shift. The track ahead is lit by the locomotive headlights. Two beams cutting through snow-filtered air, illuminating perhaps 300 meters of track ahead. At the speed the train is moving, that is approximately 18 seconds of visibility. He is watching for everything. Ice on the rail surface that will show as a sheen different from dry steel. A moose on the track. Moose use plowed rail areas to conserve energy in deep snow, Alaska rails, and a collision with a moose at speed is not trivial. A signal aspect changing from green to yellow that requires an immediate reduction in throttle to bring the train's speed down to the required level before the next signal. The radio is intermittently active. The dispatcher in a warm office somewhere monitoring the network. The crews of other trains on the same subdivision. The exchange of information that keeps multiple trains moving safely on a single track system. His hands are warm enough. His cab is warm enough. But the warmth is a managed warmth. Not the warmth of a building that holds heat easily. The warmth of a system working hard to maintain a condition that the outside temperature is constantly attacking. He checks the brake pipe pressure, normal for these conditions. He checks the locomotive temperatures. The engine coolant is holding. The fuel temperature is holding. The oil pressure is holding. Everything that should be working is working. For now, he does not think about what happens if something fails here. Not because he is not aware of the possibility. Because awareness without productive action is just anxiety. And anxiety at 3 a.m. at minus 45 Celsius in a locomotive cab is a resource he cannot afford to spend. He watches the track. He manages the train. He does his job. Dawn comes late in Alaska in winter. When the light begins, gray and gradual, the temperature has not risen. It will not rise meaningfully for hours. The cold that made the night difficult will make the morning difficult. But the train has moved. The freight has covered the distance it needed to cover. The communities ahead are closer to receiving what they were waiting for. He hands over to the next crew. He does not describe the night in dramatic terms. There was a switch that needed attention at one point. Brake pipe pressure was on the low side through one section. Normal things. Expected things for these conditions. He goes to rest. And somewhere behind him, another locomotive is already moving. Another engineer watching the same kind of track in the same kind of cold. Carrying the same kind of freight for the same kind of communities. The railroad does not close at -45. It never has. Because the people who built it understood something that most people who have never operated in these conditions do not. The cold is not the enemy of the railroad. The cold is just the environment. And the railroad was built for this environment. By people who knew what it demanded. And trained the engineers who run it to know the same. Now, send this to someone who complained about cold weather today. Because somewhere in Alaska tonight, this is what cold weather actually looks like. Hit like, subscribe if you have not already. And stay close, because what we show you next will make even this look warm.